Okay. So I can start.
Thank you. Please start.
Yeah. Thank you so much. It's my great pleasure and honor to be with you in this afternoon. Good afternoon to all of you. Now, I'll just give you some glimpse of seismological studies in India, particularly for the large earthquakes, recent large earthquakes, and the risk zones, which will be, I think, we want to share our experiences in the field of geoscience, seismology, and with engineers. Now, if we look at the history of earthquake recording instruments, we see that the first seismoscope was invented by a Chinese seismologist, sometimes 132 AD, but it was not recording earthquake, it was just giving the time and the direction of the earthquake had to occur. So this is the first, seismograph. It was in 132 AD when the first seismoscope was discovered by a Chinese seismologist, but it was not recording earthquake. It was giving only the time. I think something like our pendulum clock, which we observed, experienced during the 2001 Bhuj earthquake. It gave the time, and on 26 January that that clock stopped in a dak bungalow. So it is something like seismoscope which gives the time, but not records. The first seismograph record was established in 1887. I think now I am audio and visual also. Slides are also okay.
Yeah, yes, we are seeing the different seismographs.
Okay. So this is the first seismograph, and then the portable seismograph came sometimes in 1960s, when it was found that smaller earthquakes goes in a power law. So that D-value gives us the understanding that smaller earthquakes, the huge number of it occurs. So the portable seismograph came in 1960s, and then the digital seismograph came in 1990s. So today, and before that, with the with the analog seismograph, we had wave seismograph also. So these are the starting point with the seismological investigation from some 1897, then 1960s portable seismograph, then 1990s we have digital seismograph, and now we can record three components of the earthquake seismogram with the digital system. So these are the analogs. From analog to digital, we have come from say 1900 to 1990s. Now this is a very popular map to understand the the different major plates on the Earth's surface. From the earthquake data, from the epicenter data, you can see that the plate boundaries are well demarcated. Say this is the Pacific plate boundary. It's well demarcated with the earthquakes, and this is the mid-oceanic ridge where from the Pacific plate is spreading, and it is subducting below Aleutian Trench, Japan Trench, and Philippine Trench, and so on, Hikurongi Trench, and so on. And where the Pacific plate and the Indian or North American plate are sliding past by Stike fault along the San Andres fault. And here another plate, Najaga plate, is subducting below South American plate and causing a lot of earthquakes along the Chile coastal zones. So these are the plate boundaries that we have obtained from the earthquake epicenters. For us, this Indian plate is moving from this Carlsberg Ridge from somewhere here, moving to the northeast, and this head-on collision with the Eurasian plate and the oceanic part of the Indian plate is subducting below the Andaman Sumatra subduction zone. So Indian plate is on head-on collision, the continental plate, and the oceanic plate is on subduction below Andaman Sumatra subduction zone. So this is how, from the earthquake data, we could come to the plate tectonics concept. Now this is the Indian scenario, how the Indian plate is moving to the northeast. This is 70 million years ago. This was the Indian plate position. Now it is moving, and now the present situation is that it is on head-on collision with the Eurasian plate, and the whole Himalaya has come up. And this is the oceanic part of the oceanic bottom of the Indian ocean plate. And this is the trench, Andaman, Sumatra, the trench where the plate, oceanic plate is subducting, and this is where the two continents are on head-on collision, like in this schematic diagram where the Himalaya has come up. And where in the Andaman Sumatra subduction zone, the Indian oceanic plate is subducting and below, and then all along this subduction zone, there is a volcano line. So when you come to this, the seismicity of Indian plate, you can see all along the Himalaya, Hindu Kush zone, the syntaxis zone, and all along the Himalaya and Northeast India and the Andaman Sumatra subduction zone, these earthquakes. And along the Carlsberg Ridge, also there is earthquakes, the demarcation of the Carlsberg Ridge somewhere here. So this is the interplate earthquakes in the collision zone and interplate earthquakes in the subduction zone. But at the interior of the plate, we are getting intraplate earthquakes. And when you take the sections, say across across Northeast India, we can see that Indian plate is dipping down 200 kilometers, and across somewhere in Andaman or Sumatra region, Andaman region is down to 300, and below Sumatra down to 400. And when you take a section of the earthquakes, we can see that is going down to 660 kilometers. That means the plate is subducting and earthquakes are deeper, and we call them bend-up zone. So this is what is Indian plate situation. Collision zone earthquakes, they are shallow earthquakes, and subduction zone earthquakes, they are deeper earthquakes, and the intraplate earthquakes are within the plate, they are mostly shallow. I hope the slides are now visible and I am also audible.
Yes, sir.
Yes, it is visible and audible.
Yes, okay. Now the Indian network started, Indian observatory started after the 1897 Shillong Great Earthquake. The first seismological observatory established sometimes in 1898 December. That is almost 1899 or 1900, you say. And then after 1905 Kangra earthquake, some more stations were installed, some more stations. And by 1960, we hardly have about 15 observatories and 60 observatories by 1990. So that was our network until 1990. But after the 1993 Kilari earthquake, the digital broadband network is started since 1996. And today we have something like 200 observatories in the country, and with several clusters of many instruments. So maybe of the order of 500 observatories are now working, 200 permanent network, and about 300 in different clusters. Say, for example, Gujarat, that ISR is running something like 50 observatories, or say Wadia Institute, something like 50 observatories in the Himalaya, like that. There are different clusters of network also are there. Now I want to show you the analog and digital seismograms, how they differ. You see that for the Alaska 1964 great mega earthquake, 9.1, this was the upper seismograph. That analog seismograph looks like this, where you cannot make out the different phases of these seismic waves. You can hardly read the first arrival, but the arrivals after that are all complicated, and the seismogram is going for hours, and they're all jumbled up. It was so difficult in those days to read the phases from the analog seismograph. But now with the invent of the digital seismogram, and this digital seismogram for the 2004 Sumatra earthquake, you can see for hours and hours the wave seismic waves have come, and how they are well recorded, and you can zoom in the computer screen and you can read every phase of the seismic wave. So that is the beauty of the broadband digital seismograph that we have started since 2000, about 1000 or 1990 has come in the global network. So, and with the analog seismogram, the earlier seismologists, they have come out with this Earth's interior and different discontinuities like mantle and the outer core and the upper mantle and the outer core and the inner core, and all these boundaries were estimated from this digital, from this analog seismogram readings. But now today with the digital seismograms, there are many discontinuities are observed, but these main discontinuities which were observed by the analog are, are at the same, at same depth, means there is no difference. So you can see how the, our pioneer seismologists, they have worked with so difficult seismogram to find out the Earth's interior of the Earth. Now, once we have recorded the, earthquakes with the seismograph, we get a seismogram, we record, and from that record, how do we locate the earthquakes? That is the first job of the seismologist. And before the computational seismology came, there used to be location of the earthquake by manual method. Even till 1960s, IMD was locating the earthquakes by manual methods. And if you have the, say, this is the earthquake focus, we call it hypocenter also. And if you project it, this is called epicenter, and this is your station. So this is hypocentral distance, and this is epicentral distance. And if the arrival time between P arrival, first arrival, and the second arrival SF, if it is, say, something like 10 seconds, and then the DT, the hypocentral distance observed of 10 times of that, is minus P time. So that means there is a relation between TS and P, means arrival of S wave and arrival of P wave, about 8 times. That is a distance, the distance of this distance. So with this simple formula, we could draw the arc on the map and locate the earthquakes from different stations. We could draw and locate the earthquakes by the intersection of the. So that was an approximate epicenter, and that is why the earlier locations were all erroneous within 10 to 20 kilometers. But now the computational seismology have come, we can locate with much better computational methods, say least square method, joint hypocenter method. I cannot go into details of each method, but I just want to tell you that we can do much better location. This is routine location, and there further, precise locations by double DD, double difference method, and simultaneous inversion method. Means you can simultaneously locate the earthquakes, and you can image the earth structure below your network. You can see that how the Pacific plate, high velocity Pacific plate, is subducting that blue structure, that's subducting below the Japan trench, and how the Japan volcanic region, below the volcanoes, the velocity is low, which is understood. So this is how now the seismologist can precisely locate the earthquakes and also can image the earth structure below the network. So that is what has come from manual location. We have come to this now, by seismic tomography, we can also image earthquake structure. And this is just basic information about the earthquake magnitude and earthquake intensity scales. I think there is always confusion about the magnitude and intensity even by journalists. You see, earthquake magnitude is the size of the earthquake. That is, first Richter gave this scale, which you all know that Richter scale. And if we have the arrival interval, P arrival and S arrival, and if we have the maximum amplitude of that earthquake, this is amplitude scale, and this is the S minus P time or distance scale. And if we have this measurement, we can mark it here and mark it here, and then we can join these 2 points and get this is the Richter magnitude scale, and we can get the magnitude of the earthquake from this scale. So that was a brilliant scale was developed by Richter, which works today with much compatibility with the modern scales, at least up to magnitude 6. Beyond magnitude 6, it seems that Richter scale saturates, and we have come out with many mathematical, like moment magnitude, which is more stable. Now MW it is called, and there are of course other scales body of magnitude, surface of magnitude, and duration of the single duration, and from the intensity, macroseismic intensity, the magnitude. So there are various scales of magnitude. Now, what I want to say that today we are more stable scale. We have got MW. Now, this is the size of the earthquake, means what is the energy of that earthquake. But the intensity scale defines what is the degree of damage to that earthquake. That earthquake has caused total damage in the epicenter area and maybe some slight cracks or some fractures, in a distant area. So the intensity varies from place to place. So there are different intensity scales like Rossi scale, modified Mercalli scale, and now M.Sc scale. So that is how the whole thing has improved from manual location, then from Richter graphical magnitude to now mathematical, MW scale, and from Rossi scale to M.Sc scale. M.Sc scale is more, more descriptive and more stable scale now for the intensity measurement. Now, having done the earthquake location and estimating earthquake magnitude and mapping intensity in the field, now we want to understand how the earthquake has occurred. What is the mechanism of that earthquake? What type of fault it has occurred? Now, this, you all heard about the elastic rebound theory. This is based on the, practical observation of the California earthquake, 1905 California earthquake, where it was found that that the formation has separated. Means due to the stress, the rock has taken the stress up to a certain extent, then it has broken and rebounded, and it has been separated. So based on this observation, the Honda has given this double couple hypothesis that if we have a fault line and if there is an auxiliary plane, then its 4 quadrant will record the ground motion. Whether if this is the motion, then this side seismograph will record the up motion of the P wave, and this side the seismograph will record down motion of the ground, of the P wave. So based on these fast arrival motion, up or down due to the ground motion, we could plot them by some geological method, and we could come out a fault and solution. What is that fault? What type of fault it is? Whether it is thrust faulting or normal faulting or strike slip faulting. Of course, from this system now, hand plotting system, now we have come to wave of inversion. We can do the inversion of the seismic waves, and we can come out with the fault and solutions. And this is the symbolic representation of the strike slip solution. I will show you the next figure. You can see for the thrust faulting, when the compressional stress is dominant and horizontal, it is giving us a thrust faulting. When the tensional stress is in horizontal and dominant, it is giving us the normal faulting. And when both the stress, compressional stress and the tensional stress are horizontal, it is causing shear stress and causing strike slip faulting. And these are the symbolic representation of the strike slip faulting. This is for normal faulting, and this is for thrust faulting. But it is never, so test type of faulting we get in our solution that could be mixture of normal and strike and thrust, and this is pure normal, but this has got some strike slip component. This is pure thrust. So like that, we try to interpret the different types of nature of the faulting, how the earthquakes occur by which type of faulting, and what is their slip and what is their fault, active fault in the field. Now this is the some view of the large and great earthquakes in the Indian subcontinent. You can see during the last 200 years, say 1819 to 2024 till the other day, we have got something like 30 devastating earthquakes, magnitude 6 to 9.3, and some casualties, 2 lakhs people we lost. So, and during the first 20 years of the 21st century, we have lost human lives and properties more than the entire 20th century. With the population growth and with the lack of awareness, now the disaster earthquake is causing more and more casualties. So you can see that whole Himalayan belt is large earthquakes and great earthquakes with stars, symbols of great earthquakes, and the and the solid circles, larger circles are 7 and above. And also in the northeast Indian part and Ceylon, whole northeast region is very seismically mass active. A lot of large earthquakes, some 25 large earthquakes and 2 great earthquakes occur in northeast region. And in the peninsular shale, in the intraplate region, we can see that there are some large earthquakes in the western India and some, strong earthquakes like in Jabalpur earthquake or Koyana earthquake or Killar earthquake, between 6 and 6.5. So this is a scenario of large great earthquakes in the collision zone and subduction zone and the intraplate zone. Now, more elaborately, if you see the Himalayan, you can see from the east to west, you can see the 1950 earthquake. The MW is 8.4. It is revised to 8.4 from MS 8.6. It is now revised to 8.4 MW, means moment magnitude. And then this 1897 earthquake, Shillong earthquake. Of course, now we don't consider it as a Himalayan earthquake. Now it's considered to be an intraplate earthquake. But this 1950, and then this comes 1934, Bihar Nepal border earthquake. Then most recently, the Nepal earthquake, then the Kangra earthquake, and some past earthquake, 1803, and so on. And then this Kangra earthquake in 1905, and most recently the 2005, Kashmir earthquake in Pakistan. So these are the great and large earthquakes which has caused, a lot of loss and a lot of lives and properties in the country. And how we understand the Himalayan earthquakes? What is the tectonic of the Himalayan earthquakes? Now, as I said, that it is head-on collision between the Indian plate and the Eurasian plate, and Himalaya has come up. And here we get mostly thrust faulting mechanism. With a few exceptions, here is one, normal faulting much, much north of the MCT. And here also at the 1950 earthquake also by strike slip faulting. But mostly they are thrust faulting, because it is understandable that the Himalaya, at the collision zone, there is a compression stress, and that causes mostly thrust faulting earthquakes. And if you look at this tectonic model given by Sibar et al. In 1981, that says that the Indian basement, Indian plate is gently dipping below the, below the Himalayan wedge. You can see that that detachment of that interface between the Himalayan sedimentary waves and the Indian basement, that is called plane detachment, or M.Sc, main Himalayan thrust. And that is about 20-25 kilometers below MBT and MCT. So the Himalayan earthquakes between the MCT and MBT means main central thrust and main boundary thrust. This is the, you can see this is the main boundary thrust, and this is the main central thrust. Most of the earthquakes, Himalayan earthquakes, are in this belt, and these earthquakes are mostly between 20-25 kilometer depth, and they occur mostly on the MHT or on the plane of detachments. I mean, they're all shallow earthquakes and by thrust faulting. So that is the general model given for the Himalayan earthquake tectonics. Now, if we look at the 2005 Muzaffarabad earthquake, you can see the seismic hazards and the seismic disaster, and you can see the intensity, high intensity map here along the MBT. It is in the Indo-Kazakhstan seismic zone. That earthquake occurred here at a shallow depth, and that caused really disaster over here. And the intensity of the order of 10 for this earthquake, and it was a shallow earthquake at a depth of 10 kilometers. Now, if we look at the 1905 Kangra earthquake, you see it was earlier reported that it is magnitude 8.0, great earthquake, but now revised to 7.8, and intensity of the order of 9, and depth of the order of 40 kilometers. Now, this depth is bit unlikely in the Himalaya, so there is a lot of controversy. Now, these earthquakes caused two major seismic zones. Intensity of the order of, say, 8 to 9 Kangra, and about 7 to 8 in Dehradun. So there are two high intensity zones in this, and it was thought that it has caused another high intensity zone, but recently Hoff has found that there are two events, one magnitude 7.7 and 7.5 within minutes, and one below Kangra and one below Dehradun, and the average depth was of the order of 30 kilometers. So there are a lot of, because till that time we had no good network in our country. So these debates is still there, and there are two earthquakes now. It is mostly accepted that there are two earthquakes at a depth of 30 kilometers. Now this come 1934 Bihar Nepal earthquake. Initially it was magnitude 8.4, MS magnitude 8.4, now revised to MW 8.1, and depth of the order of 25 kilometers, and maximum intensity was the order of 10. Now again, this earthquake was not well recorded by Indian network. Of course, it was recorded by global network, but geologists, they have meticulously surveyed this earthquake, and they found that there was liquefaction and there was intensity 8 to 11 in Munger region, and they gave the epicenter somewhere near Munger at the India-Nepal border. But there is another intensity zone in the Kathmandu, and the Nepal geologists think that this earthquake occurred in somewhere here. So there is again debate on this location of this earthquake, and these are the seismic hazards. And this earthquake, I will show you in the section how it looks like in the next. Yes, it is here. Now, most recently, now we have got digital seismograph and all broadband seismometers and all. So the 2015 Nepal earthquake in central India, you can see there are two earthquakes, April 25 and another one May 12, 7.8 and 7.3, and this causes a lot of seismic hazards. Now these two earthquakes are very close and very well located, and with this most accepted seismotectonic model, this is the plane of detachment or main Himalayan thrust, M.Sc we call it, and it is said that all earthquakes in Himalaya on the plane of detachment, means above the plane of detachment. So these 2015 earthquake, two large earthquakes, they are matching fairly well that the earthquakes occurred over here. But the 1934 earthquake, this red starred here, and the 1988 earthquake, as you all know, there was another earthquake in 1988 here, Nepal border near the 1934 earthquake epicenter. These two earthquakes, particularly the 1988 earthquake, is well estimated depth of the order of 50 kilometers. Similarly, for the Sikkim earthquake recently also of the order of 50 kilometers. So there are deeper earthquakes, and they are not really M.Sc even. They are not really shallow, M.Sc or the shallow Himalayan earthquake. So there are some deeper earthquake zone to the south of MBT, and this is the network of the telemetry network data of Nepal by the Nepal-French collaboration, and that shows that there are cluster of earthquakes at shallow depth, but there are some sources in the deeper zone also to the north and to the south. So this is the latest information about the earthquakes in the Himalaya, that Himalayan earthquakes are not only particularly in the eastern Himalaya, say from east of Nepal to Sikkim and then to Arunachal, they are not really typical shallow earthquakes like that of Sikkim earthquake or that of 1950 earthquake. So there are deeper zones also in the Himalaya. And if you come to this 1950 earthquake, the Indian geologists, they could make this intensity map of the order of 9 to 10 high intensity zone over here, and the other part they could not cover because this was China's part. So this earthquake has caused, as I said, the maximum intensity zone over here. Then it is intensity goes down with the distance, and at a depth, at a say 500,000 kilometers away, you may only feel it or feel the shaking or some minor crack may have happened. But in the epicenter zone, there is a lot of disaster over here. Now, having get a glimpse of the Himalayan earthquake,